From UC Riverside. We're thrilled to have these guys. We're getting to be very, very good friends with them because they are very, very interested in medical data too. This gentleman's actually known to a lot of you, I think. In fact, you'll be seeing presentations on work this afternoon that will actually look very reminiscent of his, because a lot of us are very liberally lifting from his work and quite inspired by things he's done. This is Professor of Computer Science, Eamon Keogh. Thanks, Dave.
So, first of all, let me thank you all for coming today, and thanks for the invitation. It's a great joy to be here. Oops. What did I do? Oh, I won't touch it again.
It was the stop. That's the red thing.
Okay, no. I'm not a high-tech person, as you can tell. Okay, let me get the outline of my talk. The first 5 minutes are going to be a little bit boring. We're going to give you a kind of a classroom lecture on what MDL is and what time series motifs are. And then I'm going to show you that we can use those two ideas to do some very clever things, hopefully with your medical data. I'm actually going to start and end with take-home lessons, and those are: don't try to explain all the data. First of all, you're probably doomed to failure if you do. And secondly, you might actually miss some local gems. This makes sense later on. Next thing is, parameters are bad. What I mean by that is, if you have an algorithm, there's lots of tweaks and twists you can make. That's probably actually a bad thing, not a good thing. Because you'll end up tweaking too much, and it'll work beautifully on this Hispanic, obese, tall boy, and not work on this young African-American girl, or whatever it might be. And it ain't necessarily so. Unfortunately, in my area, data mining, most papers are wrong. And you need to be very, very careful when you read literature to pull out the real gems. Again, I'll show you examples of this. And then finally, time series motifs are really useful, and this MDL stuff can be useful to guide data mining. So what is MDL? MDL is a principle of philosophy that says the best model for the data is the one that can compress it the best. So yesterday, Stuart Russell showed us a very complex model. Suppose that Randall shows us a different model. How do we choose which model to actually use? It's a tough question. So MDL says, take both models, use those to compress the data in some sense. The one that makes the data smaller is the winner. Now, if you have two models, that's not too bad. You might actually have 1 billion models made by an algorithm, and so choosing them with MDL can be actually quite useful and clever. So I'm going to show you a very contrived, silly example of this, but it's actually worth seeing once. So here I have D data, and it's a very silly contrived string. And DL is the description length of the data. It's simply how many bytes it takes to make this data. So it took 93 bytes to actually represent this data. It's basically just 93 ASCII characters. So this is the length of the data originally. And now MDL says, let's try and compress it a little bit. So one trick I can do actually is I can pull out the string David. I can give it a special code which is short called 1. And I can replace occurrences of David with just 1, 1, 1. And of course, there's different spellings of David here, so I actually have to encode those two separately. And so now, the length of data here actually is much smaller, because I've saved all these bytes here. It's only now 80 bytes. But I have some bytes for my hypothesis, my explanation, my model. When I add these together, I have only 88 bytes. I've actually squeezed the whole thing together. I can do it again, this time pull out, let's say, Peter. And once again, the overall data gets smaller. My hypothesis gets a little bit larger, but I still win if I add the two together. The description length of the hypothesis plus the description length of the data given the hypothesis is only 83 bytes. And as it happens, I'm done. No matter what else I do from now on, let's say, for example, if I tried this model of the data, it would actually make my data larger, not smaller. So MDL would say to me at this point, okay, this is the model of your data. And as it happens, this is true, right? The model of the data was somebody, me, contrived a sentence that uses the word David and Peter a lot. That's what the model of the data is, and that's what MDL says it is. Now, of course, it's a very silly, contrived example. MDL is actually used in much more complicated and sophisticated ways to do much more wonderful things, but it kind of gives you the idea of what's going on here. If you can compress the data, the way you compressed it is really recurrent structure that could be actually useful. And it's just actually, as simple as this actually is, it's actually not that trivial, because if you give a data miner data, the first thing to do is just do k-means clustering. It's the first thing we always try. If you do k-means clustering this data, you might pull out all the substrings, there's a little box here, cluster those as k-means, and you might get, for example, for k equals 20 this, or k equals 40 this. And it's not obvious from this or this what the structure really was, right? This actually does pull out the cluster here, David's, but it also pulled out this cluster here, which is totally meaningless. It's a coincidence. So MDL is a wonderful thing. And where I'm going with this talk today actually is that MDL has been used for many years, but it's always been used for discrete objects like DNA, ATCGs, English letters, computer code, protein strings, and so on and so forth. It's always been tricky to apply MDL to time series. And as it happens, I think we can now do this. I think it's actually a very, very cool and wonderful thing. And the other brief review actually is what are time series motifs. So I don't have any medical data, so I have something almost as good. I have these little insects here. And these guys are innocuous to us, you might think, but they cause about $10 billion of damage every year to plants. This guy is going to go on a plant here. He's going to drive a styler into the plant, suck out some sap. He goes from plant to plant, spreading diseases. A very nasty guy. This is actually one of about 8,000 species of leafhopper. So we can actually wire these guys up. We can actually hook a gold wire to their back with some glue. We can measure the resistance to a plant. And now we have an insect, we have time series data. And this is a small snippet. We actually have terabytes of data. Not as much as you have of ICU patients, but we still have quite a bit of data here. And the question is, what do you do with this data? It's so nasty and complicated and structured. And one trick would be to do time series motif discovery. So we're going to look for repeated patterns in this data. Now you can see them at this scale here. If I zoom them up larger, here and here is a repeated pattern. And when you see it, they're so similar, you can't believe it's a coincidence. Something has happened in the world. As it happens, we can look at the timestamps, we can go to the video of the insect, and we know exactly what's happened here. This is actually the moment of penetration of the stylet. The insect pauses for reasons people don't know. It drives the stylet in, it pulls it out to get the sweet spot in the vein, and it begins happily sucking the sap out of this thing. This actually was known. The next one we found actually was unknown. So again, this is actually from a different time series, but the same insect. Here's a very complicated pattern of behavior. Happens multiple times. What does it actually correspond to? It turns out that every now and again, the insect that sucks at the sap has to get rid of some sticky water called honeydew from its anus. And so when it builds up a bead of this stuff, it shakes it off very quickly. Very, very quickly. You really can't see it by eye. And this is actually the insect shaking his butt to get rid of the water. Actually, what it actually ejects is literally manna from heaven. That's what the Bible talks about when it talks about manna from heaven. It's the sticky little stuff. A obscure but true fact. Okay. So obviously, you're probably not interested in insects like I am. You're interested in, we've seen photographs like this all day yesterday. You're interested in patients. But the principle's the same. You probably have more data than we do. You probably have discrete data and text data. You have, a complicated, nasty problem. But in principle, it is time series that streams off devices, whether it's insect or a person. And the question is, are there motifs in this data? And would they be useful? And actually, in the last few years, people have been writing papers using motifs. So there is some partial answer to this. And I'll show you my additional answer today. Okay, what about now, we're done with our review. What about clustering in medical time series? So here's a well-set paper about data mining in a time series. And they're trying to cluster this very trivial section of heartbeats here. It's a very, very simple problem, as you might imagine. And they basically run something like this k-means thing. And the cluster they got was this guy here in black and white. And amazingly, the cluster actually is quite bad for an incredibly trivial problem. So look here. So forgive me if I make a medical mistake here, but at the beginning of this P wave here, there's a little rise. But it never appears in the original data. What actually happens here is that there's actually not 5 heartbeats here, there's 5.5 heartbeats. And the model trying to explain the half a heartbeat, it can only explain it by having a bit of a bump here, which does not exist in the real data. It's just an artifact of how they clustered this. So this is an example of don't try to explain all the data. You explain all the data, you actually introduce artifacts. So could I do better? Well, here's some data. I'll tell you what it is in a few minutes. I'm going to use an MDL-like principle to actually cluster this. So again, D is my data. And my first trick is to find motifs. I love these motifs. And the best motif actually is A and B here. And what I can do, actually, I can say, well, A and B are so similar, if I subtract one from the other, I get almost a straight line. I'm going to call that C. And I can think about how could I encode this data using C. What I would do, and this is only internal. You don't see this, of course, like as a doctor or what have you. is I remove B here and save a lot of bits from removing it. I put in C instead, but C is very small, takes very few bits. And then I have a back pointer to A. So when I want to make that time series again, I simply would take C, go back to A, add A to C. I would now have B exactly, but I've actually saved some bits here. In other words, the description length of my hypothesis, which is actually the time series here, plus the description length of the data given the hypothesis is actually now smaller. I've saved some data. And I could do this again. I have some choices. I could actually add the red, look a bit like the blue. So I could add the red to the blue. Or I could have a new motif, these pink guys here, and I could add those. So there are some choices, there are some search. But actually, Stuart Russell taught me how to do, not directly, reading this book, taught me how to do search. I can do search. So I'll search for all possibilities, and I will find the best MDL representation of the data, and here it is. So at every stage here, I save some bits, save some bits, save some bits, save some bits. At the last step here, actually, I would not save bits. I can't squeeze anything else out of this data. I have to stop. And here's what I stop with, this cluster in here. And subjectively, actually, this is correct to me. It looks pretty good to me. But is it really meaningful or true? Well, I'll tell you what the data actually is now. The data actually is speech translated to a time series with a trick called MFCC. And the data actually was Chorus of the Bells by Edgar Allan Poe. So if I brush the colors on the time series onto the text, you can actually see the clusters kind of make sense. Actually, here they're sorted by clusters. So one cluster is of the bells, bells, bells. Another cluster is the throbbing of the bells, the sobbing of the bells, the tolling of the bells, and so on and so forth. So I really actually have clustered this data correctly. And I did this with no parameters, no human intervention. I dumped the data into a black box. I walked away, and the algorithm said, this is what this is all about. Does it work for medical data sets? The previous example is so trivial, I thought it's a bit more complicated. Here's some examples. And at least to my eyes, it's worked reasonably well. Here I found two different kinds of clusters in this medical data set. I'm guessing the red one is a normal heartbeat, and this pink one is an anomaly. I'm sure somebody in this room could tell me which exact kind it is. And notice actually in both cases, there are small amounts of the data that we haven't actually explained. And again, I think this is actually the key. If we're forced to explain all the data, we're going to do a bad job. If you let me simply say, I don't know, or I don't care, I've really some chance of actually doing a good job on this. Okay, so clustering is very nice, very useful trick for all kinds of algorithms. But what about prediction? Prediction is really cool, right? If we can say what's going to happen in the next 5 minutes, that's useful. Especially what's going to happen is insulin shock or a seizure, whatever it might be. So let me just contrast prediction and forecasting. Forecasted actually is always on. It's always making a prediction about 2 minutes out, 2 minutes out, 2 minutes out. And again, this is actually very hard or impossible because you have to explain the entire universe at all time steps. In contrast, prediction actually only occasionally says something. It always looks at the data, but only once in a while to say, now I know what's going to happen. This was going to happen. And this actually, I think, might be tenable. So there are three kinds of papers on prediction and data mining. There's the dubious, the wrong, and the not even wrong. So let me show you some examples. Just one, actually, for brevity. This doesn't show up very well, but I apologize for that. This is actually not an obscure paper. This is a paper by three of the biggest stars in data mining in the best conference, and they won the best paper awards. This is actually a very nice paper, shall we say. And they do some prediction, and it's hard to see, but basically they say, if you see this time series here, then within some few seconds you will see this time series here. And how confident are they? Well, they measure this with three numbers: support, confidence, and something called J measure. So they found these rules. People loved this paper. There's many follow papers and so on and so forth. And then in 2004, I actually proved this couldn't work logically. In particular, the algorithm is a random number generator. The input and the output are totally independent of each other. And I kind of showed it in a cute way. I asked them to cluster or to predict my data, and they actually found very similar rules for my data. And the support, confidence, and J measure are all about the same. But the thing actually is, my data was quantum mechanical random walk. There are no rules in my data unless quantum mechanics is wrong, right? But the strange thing actually is, not only was it published once and very successful, but there are several hundred papers that actually made it a bit faster, a bit better. But they're taking a random algorithm and making it slightly faster random or slightly more random. It makes no sense. And by the way, actually, that paper was only wrong, right? It wasn't not even wrong. Those papers, I'm not going to show you. They're done with too much fun. Okay. So rule prediction or rule discovery is very, very difficult, but can we do it And I think the answer is we can do it, and the secret sauce is going to be MDL and time series motifs. So here again we have the time series. I want to find rules in this. And my trick is going to be, of course, again, to find some motifs in here. So here I found a motif. And I'm going to simply take this motif, I'm going to slice it here. And the average of the left side, I'm going to call the antecedent. The average of the right side is a consequent. And this is now my rule. My rule says, if ever in the future you happen to see this shape here, then you're going to see immediately afterwards this green shape here. And the time it's going to take is going to be about 0 seconds. So it'll happen immediately. So now I have a rule. And I can monitor the time series at an ICU or an insulin pump or whatever it might be for the rest of my life. It's very cheap to do this in terms of CPU time. And if ever I see this shape here, I immediately say the green thing happens next. And as it happens, it does work, it seems like it. So here's a real example. Later on in the time series, we see a very similar shape to this kind of yellow shape here. And I predict immediately the green thing will happen. And as it happened, the green thing did happen nicely. And once again, to give you some context to this, the ground truth, back to our friend Edgar Allan Poe. This actually was the first verse of The Raven. And so I tested this then on the rest of The Raven. And so, as it happens, the rule corresponds about to "at my chamber door," this nice refrain in this poem, which does happen 6 more times in the poem. And we fire 6 times. And we never fire by mistake. We never actually say it'll happen, and it really didn't or shouldn't have happened. So one question about any kind of rule you might have in a medical situation is, how will it generalize? Again, is it going to generalize from the tall kid to the skinny kid to the diabetic to the whatever it might be? And so, for example, for this case, are we invariant to who's speaking? And the answer is, if it's a North American male with a deep voice, yeah, we're pretty much okay, right? If it's a female, it's not going to work, unfortunately. What about rate of speech? Faster or slower? We're pretty invariant to that, and we can actually improve that. What about foreign accent? Unfortunately, no, right? If it's someone with an English accent or an Irish accent, it doesn't work quite so well. We might have to relearn a rule or readapt with that. So actually, in the previous example, when the rule fired, it immediately happened that the new shape would appear, but that might not be the case. And here's a nice example of that, which I found. I had a student wear a sensor. Actually, an iPhone is basically a sensor to measure acceleration. And acceleration in the X and Y axis is very common. In the Z axis is very rare. And here's an example I found. That in the Z axis, if you see this pattern, then within 4 seconds you would see that pattern here. And what it corresponds to is my lazy student using the elevator. So normally there's no acceleration in the Z axis. He gets into the elevator, and there's an acceleration up. You feel a bit heavier for a second, you get this bump. And then when the elevator stops, you have a little bit of a lurch, and you get this positive bump here. And my point actually is here that if I learn this rule on my building, which only has 4 floors, the max lag is going to be 4 seconds. But of course, if I do it in your building, you have more floors, I'm going to have to hand edit this. It's just actually kind of a generally interesting thing. If we find medical rules in a particular domain, could you actually, as a doctor, look at that and say, I believe the rule, but to make it work for girls as well as boys, I'm going to have to smooth this or change this or modify this in some sense. So again, I've already taught you to be very dubious about rule finding and data mining in general, but I really actually think this actually does work, at least in some domains that we've tried it on. Here's a nice complex domain we've tried it on. These are zebrafinch songs, and we found this little rule here. If the zebrafinch sings this, then he will immediately sing this. And then we tested it on later data from the same zebrafinch, and it's complex, nasty data, but occasionally he does go into this refrain, we predict, and we are correct. And how does this generalize? It works for him. It works for his son that was raised within an earshot of him. It doesn't work for other zebrafinches. So with some more experiments, we can actually maybe tease out nature versus nurture. If we take the son and raise him separately to the father, is the rule actually telling us about genetics or telling us about culture and copycat behavior? Okay, my kind of final example is classification. So we've done clustering and rule discovery. And I'll start an apparent digression. If I showed you these leaves here, which one are stinging nettles, which one are false nettles? An important problem if taking a walk in the countryside, as it happens. So as it happens, color is not particularly useful to tell you the answer. And shape is not useful either because, for example, they can have insect bite damage and so on and so forth. So the first trick actually is you can make a shape into a time series, believe it or not, in a kind of a fake way, We can simply walk around the outline and measure the local curvature or measure distance to the center. And then in 360 degrees, we have a short time series. And instead of trying to explain the entire time series, which I already pointed out could be dangerous, we're going to kind of find a special kind of motif, a supervised motif called a shapelet, which in this case happens to be this red guy here. And my claim actually is that all of one class has a shape close to this red thing, and all the other class does not. And the intuition, actually, we can brush onto the original shapes. For false nettles, the angle between the leaf and the stem is quite large, but for stinging nettles, it's quite close to 90 degrees. And so based upon this, we can do one of our favorite tricks of machine learning people or data mining people, build a decision tree. And now from new leaves or shapes that come in, we simply do this test very quickly, and we say false nettle or stinging nettle. And we're able to ignore the insect damage and so on for the most part. Okay, just for fun, I mentioned this actually works beautifully. And it has a nice property that actually, it kind of not only classifies the data, but it kind of tells you why it classified the data. So here we built a classifier for projectile points. We have 1 million of these on our campus, unbelievably. And not only does it actually classify very accurately, but it kind of says, oh, I think this data set is in its class because it has this little side notch here for tying the arrow on, whereas this guy here has a notch here at the bottom where it jams into the stem. So it kind of gives us some hint as to why the data is in each class, not only actually as a good classifier. And here's another example of that. This is actually a very famous problem in time series. People all over the world work on this one. It's called the gun, no gun problem. And we're actually more accurate than the best classifiers in this. And part of the reason is because, as I mentioned before, everyone else tries to explain the entire 1 second or 1.5 seconds of time series. But actually, most of it is irrelevant. The supervised shapelets actually only zoom in on local parts and explain those. And it explains this part right here. And what it happens to correspond to is the actualist here has a gun in her hand, a fake gun, and has a bit of a weight or inertia. And so when she points the gun, it kind of overshoots a little bit. And the small overshoot in here is this little dip here. And we can use it to actually predict the gun versus no gun class. Okay, so I'm going to finish up here a little bit ahead of time, answer questions if I can. So the take-home lessons, once again, are don't try to explain all the data. And I mean that kind of at every level, the low level of algorithms, maybe at the higher level. You probably aren't going to be able to explain every child in the ICU or every moment of one of the time series. Or it's just an intrinsically difficult thing to do. And you're going to miss the local patterns that really are exploitable and useful. Parameters are bad. So all the results I've shown you today did not require any human tweaking or intervention. You take the data, you put it in a box, you walk away, you come back, and it gives you what it gives you. You could maybe go back later on and get new sensors or change things a little bit, but it doesn't let you change the data too much. And it's actually very important so you won't overfit. And I hate to give a kind of a negative note here, but be cynical when you read data mining papers. There's a lot of very dubious ideas out there. At the very least, don't assume it's true because it's in the paper. Do some independent testing. And then finally, of course, my claim actually is these time series motifs are really, really useful things. And I think actually want to see more and more of them, hopefully in medical domains. And the MDL is a very useful tool to guide data mining. Thank you.